Hello and welcome. In this video, we are going to talk about derivatives of inverse trig functions. How do we find the derivative of arc sine, arc cosine, inverse tangent? And that really is the only topic that we're going to cover in this video. So we'll do some basic ones, and then we'll do some that involve the product rule or the chain rule and different variations of those functions. But again, the goal in this video is that we can take the derivative of a function involving an inverse trig function. So let's jump right in. So we're actually going to derive a couple of these inverse trig derivatives. So we're going to start by just saying, let's let y equal arc sine of x. And just as a reminder, arc sine of x, this is exactly the same thing as if it's written as inverse sine of x. And it's sort of personal preference on which way that you write it. So if I let y equal arc sine of x, and my goal is to be able to say y prime equals something, my issue here is I don't know what the derivative of arc sine is equal to. So one thing that we can do back from pre-calculus is, since we're talking about y is equal to the inverse of sine of x, we could flip our x and y to write this as an inverse. So this is the same thing as saying x equals sine of y, right? How do we deal with inverses? We flip our x and y's. We're taking the inverse of both sides, so to speak, and that would give us that x is equal to sine of y. Now, if I wanted to take the derivative of this, I'm going to take the derivative of both sides with respect to x. This side is going to become 1. The derivative of sine is cosine of y. And then we need to multiply this by y prime because we took the derivative of both sides with respect to x. So now if I want to solve for y prime, I get that y prime is 1 over cosine of y. Well, here's the problem. I want my derivative to be in terms of x. And right now, I have y prime is 1 over cosine of y. So I need to get creative here, and I need to find a way to relate x and y together so that I can sort of rewrite this in terms of x. So if we draw a right triangle, at this statement here, sine of y is equal to x. And remember, sine is the same thing. Sine is opposite over hypotenuse. So we're saying that sine of y, that means y is our angle, is opposite over hypotenuse. And in this case, that is equal to x. So opposite could be x, hypotenuse could be 1, because if I take the sine of that, sine of y would be opposite over hypotenuse, which would be x over 1, which is just x. So this triangle that we have created here makes this statement true. If sine of y is x, then y is my angle, opposite is x, and hypotenuse is 1. And how do we find the missing side of that triangle? We just do the Pythagorean Theorem, right? 1 squared equals x squared plus that missing side squared. So if I want to solve for that missing side, I would get that missing side is 1 minus x squared, the square root of that, if I was going to solve for question mark there. And why does this help us? Well, now I can rewrite this fraction as, I can rewrite cosine of y in terms of x. Well, cosine of y is going to be adjacent over hypotenuse. And in this case, adjacent is what we just found, the square root of 1 minus x squared. And hypotenuse is 1, so cosine is just the square root of 1 minus x squared. 1 minus x squared. So this is our derivative of arc sine. So we could write d dx of arc sine of x is equal to 1 over the square root of 1 minus x squared. We're going to do just one more proof of these. We're going to do the one for arctangent. If you're interested in seeing all of the proofs, check out my BC video on the derivatives of inverse trig functions. I think I do more of them there, but you'll notice that once we get all of them in one place, that cosine, cosecant, and cotangent are just the reciprocal, they're just opposite in sign from those originals. So proving all 6 of them just feels a little bit redundant. Even proving 2 of them might feel redundant. But let's just do one more for good measure. We're going to do the derivative of arctangent. So we're going to start the same way. Let's let y equal arctangent of x. And again, if we want to find the derivative of arctangent, we need to make it not look like arctangent right now. So we could rewrite this as x equals tangent of y. Our goal is to find y prime, so I can take the derivative of both sides. The derivative of x with respect to x is 1. The derivative of tangent of y is secant squared of y. And then we need a y prime, again, because the derivative of tangent of y with respect to x, that's why we need to tack on that y prime. So if I solve for y prime, I get that y prime is 1 over secant squared of y. And secant squared of y is actually just cosine. Sorry, 1 over secant squared of y is cosine of y. So we again have this same issue that everything is in terms of y instead of x. So let's draw our right triangle. Again, using this fact, tangent of y, well, tangent is opposite over adjacent. Tangent of y is x, so this is going to be x over 1. And we can again use Pythagorean Theorem to find out what that hypotenuse is. So in this case, y prime is equal to cosine of y squared. And cosine of y would be adjacent over hypotenuse, so 1 over the square root of 1 plus x squared. That whole quantity is going to be squared. And when I square that, the denominator is going to lose that square root. So I'm going to end up with y prime is equal to 1 over 1 plus x squared. Or I could say the derivative with respect to x of arctangent of x is equal to 1 over 1 plus x squared. So now let's go ahead and take a look at all 6 of these inverse trig derivatives together. So here are the 6 inverse trig derivatives. We just came up with the derivative of inverse sine and the derivative of inverse tangent. And one thing that you should notice that already looks really weird in comparison is that all of these inverses have u instead of x. And that just means that if you have a function, like let's say you had sine of 2x, you can think of u as being that inside function, which means u prime in this case would be 2. Sorry, not sine, but arc sine of 2x. And that will help you deal with the chain rule that could occur if you have more than just inverse sine, inverse cosine. So that's what these u's are doing. They're applying the chain rule. So whatever is in the place where u is within your equation, you can think about that as u and u prime, or identify u prime, so that you can use these shortcuts. Now, for regular calculus, you do not need to memorize these 6 trig derivatives, but if you are taking AP Calculus, these are things that you need to know. You won't be given them on the AP test. So now that we can see them, and as I mentioned, but now you can see it better, cosine is exactly the same as sine, except there's a negative, and I'm actually usually going to put that negative up in the numerator. Cosecant is exactly the same as secant, except it's opposite in sign. Cotangent is exactly the same as tangent, except it's opposite in sign. So we don't need to do the same proofs or even really memorize something different other than that they're all off by a scale factor of -1. And the other weird thing that I just want to point out to you is that secant has this absolute value, as does cosecant. And that absolute value is coming from the fact that when we work with, or when we go about the proof using secant, the derivative of secant is secant tangent, and that value is always positive because secant and tangent have the same sign. Because of that, when we rewrite, when we take the derivative, we need to account for that by putting absolute value around that value. So that's where it comes from. If you want more of an explanation, I'm happy to do that for you. But here in this video, I think the goal is that you can use these inverse trig derivatives when you're given a problem. So let's go ahead and look at some examples, and I'm going to leave these formulas or these derivative rules up top so that you can look at them while we are working through these practice problems. Okay, so here we have 2 examples. So what I want you to notice is that, as I had mentioned, we have a function inside arc sine. So what we're really doing is applying the chain rule. But if you use this formula up here with the u's in the places where they're at, that's already accounting for the chain rule. So in this problem, you can think about this as u is equal to 2x, because that's the inside function, and u prime, the derivative of that, is just going to be 2. So when we apply the formula, I'm going to call this y prime. You could also call it dy dx. We're going to take this up here, but we're going to plug in u and u prime. So u prime is 2 over the square root of 1 minus, and then u in this case was 2x quantity squared. And you could simplify this if you want to just say 2 over the square root of 1 minus 4x quantity squared. But identifying u and u prime is going to make it easier to work through this process. So why don't you go ahead and try number 2. I'm going to give you the hint here that we have our u being 3x. So pause the video, use this inverse tangent formula, and identifying that u is equal to 3x to try and work through this one on your own. So hopefully you have had time to work through this. In this case, y prime, or dy dx, is going to equal, well, u is 3x, so the denominator is going to become 1 plus 3x quantity squared, and the numerator is going to be u prime, which in this case is just 3. So if I rewrote this just so that it's all a little bit more simplified, I would have 3 over 1 plus 9x squared would be that derivative. So if our inside function is something really basic like this, identify your u and your u prime, and then you can work through the chain rule simply by using the rules up here. So let's do one more like those two, and then let's add on maybe the chain rule in a little different of a format. So on number 3, which if you're feeling confident, go ahead and pause the video and work through on your own. On number 3 here, u is going to equal x to the power of 1/2, which means that u prime is 1/2 times x to the power of negative 1/2. So y prime, or dy dx, we're using cosine inverse here, is going to be negative u prime, which is 1/2 x to the negative 1/2 power, over the square root of 1 minus u, which is x to the power of 1/2 squared. And I'm going to clean this up just a little bit. I'm going to move the 2 from the 1/2 in the denominator, but I'm actually going to leave x to the negative 1/2 in the numerator. So this is over 2 times the square root of 1 minus x, since x to the power of 1/2 squared is just x. This looks a little bit easier, a little bit nicer to look at. You could also, if you wanted to, move x to the negative 1/2 power down below, but I'm going to leave it just like this. So what I want you to see on number 4 is that we have a chain rule situation, but not in this u prime u way. On number 4, the outside function is just regular tangent, and we know that the derivative of regular tangent is secant squared. The inside function is our inverse trig. So we are going to apply the chain rule for number 4. So y prime is going to equal the derivative of tangent of something is secant squared of that something, and that something doesn't change, so we still have arc sine of x here. So secant squared of arc sine of x, that's dealing with the outside portion of the chain rule, and we need to multiply that by the inside derivative. Well, the derivative of arc sine is just 1 over the square root of 1 minus x squared. And I might clean this up just slightly by writing this as 1 fraction, and the denominator being this square root of 1 minus x squared. So make sure that when you start the problem, you really take the time to see what's going on. Is there a chain rule? Is there a product rule? What's the inside function? What's happening with the outside functions before you jump right in? Take the time to figure out the approach that you're taking on the problem. We're going to do 2 more examples together, and then we're going to wrap up. Okay, here we are with our last 2 examples. If you are feeling confident, I encourage you to pause the video and work through these on your own. I'm going to give you a hint that might help you feel more confident. On number 5, you're going to need to use the product rule for this first portion, x times arctangent of x. On number 6, you're going to have to use the chain rule. However, since the inside function is inside inverse cosine, you really just need to use u prime in the way that the arc cosine formula already does. So you're going to use this formula. You don't have to apply the chain rule if you start by defining u to be the inside function and u prime to be its derivative. So if you're feeling more confident now, pause the video and work through these on your own. Otherwise, let's work through them together. Y prime is going to be, well, the derivative of the first function here, x, is 1 times keep the second function the same, arctangent of x, plus, because product rule, x times the derivative of arctangent, which I can find right here, is 1 over 1 plus x squared. And then we need to take the derivative of this negative 1, which is just 0. And then I'm just going to rewrite this so it looks a little bit nicer. Arctangent of x plus x over 1 plus x squared. That would be our derivative. For number 6, our u is going to be, that looks like an A, let's try again. U is going to be x squared minus 1, so u prime is going to be 2x. So y prime is going to equal, looking at the derivative of inverse cosine here, negative u prime, which is 2x, over the square root of 1 minus u, which is x squared minus 1, quantity squared. Now, we are not multiplying by the derivative of this a second time because we already covered that when we found u prime. So by identifying u and u prime within inverse cosine, we're already applying the chain rule. So if you multiplied by 2x again, it would be like you applied the chain rule twice, and I don't want you to do that. So key ideas in this section. Working with the derivative of different inverse trig functions, making sure that you know how to use their formulas, how to identify if there's a product rule, a chain rule, even a quotient rule going on, and how that changes the steps that you need to take in the problem. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.